the Topos Institute Colloquium. Today we're very happy to have Xiao-Gang Wen talking to us about symmetry as braided tensor higher category. So please, Xiao-Gang.
Okay, yeah, thank you. Thank you for the invitation. And so today I'm going to talk about symmetry, basically. And usually when we say symmetry, one naturally think about a group. But now in recent years, we realize that the symmetry are related to the braided monodal category. And but here I use the braided tensor category because the category may have infinity object. So we say maybe that's tensor. Maybe monodal means a finite number of objects. And so please feel free to interrupt me and ask questions. I'll be very happy to answer any questions during my talk. Okay. So we know that symmetry are really a very important phenomenon in both mathematics and physics. And so in particular, classical systems like this pattern wallpapers, they are invariant under certain transformations. And those transformations can be composed and form a group. So for a long time, when we say symmetry, we actually mean group. So these two words are just very closely related. And for example, you can classify finite symmetry by classify finite groups. And this is actually classification of finite group is one of a really great achievement in mathematics. But however, our world actually is not classical. Our world is quantum, really. So in a quantum system, there is also some structures we can associate to symmetry. And so we call the quantum symmetry. And for a long time, people also think quantum symmetry, just like classical symmetry, are described by groups. But in recent years, we find that the quantum symmetry can often go beyond groups. And so this led to this story that actually quantum symmetry is described by this braided tensor category, or maybe a braided monodal category. Okay. So because of a lot of mathematicians in the audience, so let me define what is a quantum system. And so quantum system basically is a model. It's some kind of mathematical model to our physical world. Okay. It turns out that our physical world can be modeled by two things: a Hilbert space and a Hamiltonian. Okay, or any physical system can be modeled by the Hilbert space and a Hamiltonian. But however, there's a Hilbert space, and it's kind of special. So the Hilbert space have this tensor product decomposition. So for example, we may have a graph that's kind of model the space. And then on each vertex graph, we have a finite Hilbert space, like a C to the K. And then the total Hilbert space is a tensor product of all those so-called local Hilbert space on each vertex. So therefore, the Hilbert space with a tensor product decomposition is a wonderful structure describing quantum system. And then in this structure, we have a notion of a local operator. Local operator basically is operator act on each on-site Hilbert space, or maybe on some nearby Hilbert space, is the tensor product of a nearby Hilbert space. And so then this local operator can multiply and add. They form algebra. So this is called the algebra of local operators. And then the dynamics of the system, the physical state are described by vector in the Hilbert space. And the dynamics describing how this vector evolve, how physical states evolve in time. And this dynamic is controlled by a Hamiltonian, which is a sum of a local operator. So there's some locality to the Hamiltonian. So this sum of a local operator. So all those concepts are needed. And this local operator really means that the Hamiltonian only involving interaction for nearby degree freedom. There's no long-range interaction. So that's basically define a mathematical structure which a model we believe any physical system. So I'm a kinematic physicist. So my job just to study this kind of thing. This Hilbert space with a tensor product structure and also the Hamiltonian and their properties. Okay. Remember, the dimension actually is a very important notion. You know, we have a physical system, but that's a one-dimension, two-dimensional, or three-dimensional system. The dimension of a physical system actually is given by the dimension of the graph. So this graph is some kind of triangulation of some kind of n-dimensional manifold. And so that gave us a sense of a dimension for the physical system. So that's basically an introduction of a quantum system. And for example, let me describe a quantum system now with a symmetry. And so for the example, we describe a quantum system with a Z2 symmetry. Z2 is a group. But we're using this old group theoretical point of view to describing this symmetry. And for this particular quantum system, our on vertex Hilbert space is two-dimensional, and we have a basis which we call spin up, spin down. It's up and down, just two bases of this two-dimensional Hilbert space. And so certainly choosing such a basis really also we also hint this kind of system, this kind of Hilbert space actually describing a so-called quantum spin system. Or in other words, it's a kind of magnetic system where this spin is really carried by electron. Electron have a up state and down state. And this degree of freedom is modeled by this two-dimensional Hilbert space. So here we are really talking about the quantum magnets. Okay. And if this quantum magnets of this quantum system have a Z2 global symmetry, then that means there is a symmetry transformation, which basically is a tensor product of this X operator on every vertex. This X operator just flip up and down spin. They map up to down, map down to up, just this spin flip operator. And obviously, this W squared equal to 1. So therefore, this W generates a Z2 group. So that's a symmetry group and a symmetry transformation. And then we can define the algebra of a symmetric local operator. That is an operator, some local operator which commute with this Z2 symmetry transformation. And then this symmetric operator, symmetric local operator, also form algebra. So they call this algebra of a symmetric local operator. Then the Hamiltonian with the symmetry is more special. It will be the sum of a local symmetric operator, means operator commute with this W transformation. So this is this gave us so-called Hamiltonian quantum system with a Z2 symmetry.
So Xiao-Gang,
So this is standard story. Yes, please.
does it mean that if you watch the system evolve, or you flip it and then watch it evolve, you get the same evolution?
So
okay.
So suppose you have a vector, this vector evolve. Then this vector, you can do the Z2 transformation on this vector. Then that vector would have a kind of a mirrored evolution. Yeah. And in particular, like the eigenvector of the Hamiltonian is also eigenvector of this symmetry transformation. So so there are certain another way to say eigenvector of this symmetry transformation would evolve as eigenvector with same eigenvalue. So they evolve within this eigenspace of same eigenvalue. So the point is that this when you have a symmetry, the quantum evolution, the quantum dynamic is constrained. It's not just arbitrary evolution. It's a more organized, a more constrained evolution. And so therefore, this constrains the physical property of the physical system. Okay. So this is an old picture. But from my description of the old picture, we realize that actually the symmetry transformation is not important. You know, dynamics are controlled by a Hamiltonian. And the Hamiltonian is a sum of a so-called symmetric local operator. So it's this collection of a symmetric local operator is important, and that will determine the constraint dynamics. And how we select those subset of a so-called symmetric operator is not that important. So therefore, we can just ignore the symmetry transformation and ignore the group. We just pick a subset of local operator. And then we consider algebra generated by this subset of local operator. And we call this a local operator subalgebra. So this is an important concept. We just pick any local operator subalgebra. Then that will correspond to a symmetry. So therefore, we can define symmetry via operator algebra of the local operators, not via a transformation and not using groups. So this is a very simple observation, and that's where generalization comes from. For example, if you consider if our algebra includes all the local operators, that means no constraint. So that means trivial symmetry or no symmetry. However, if our algebra are generated by a subset of a local operator, and which do not include all the local operator, then that means we have some non-trivial symmetry. And then the time evolution are only generated by this subset of a local operator. So their dynamics is constrained. Okay. So this is kind of more general setting of the symmetry. You know, when you're using the transformation to define quantum symmetry, then we know the mathematical framework for the transformation is group theory, because transformation can be composed in the form of group. We can use group to describe or classify different symmetry. Now we make a shift. We want to use a local operator subalgebra to define symmetry. Then there's an issue. What kind of mathematics which is classify or describing this kind of symmetry? So so that is basically the story. Within this description, certainly there's this equivalent operator algebra would correspond to equivalent symmetry. You know, sometimes the operator algebra may have different realization, but at the algebra level, they are kind of equivalent. Then we want to call this those equivalent algebra as equivalent symmetry. However, you know, in physics or maybe also in mathematics, the equivalent symmetry are really may have very different meanings. So here I just say holo-equivalent symmetry to refer to the equivalence coming from this operator algebra equivalence. So we have this more precise notion of a holo-equivalent symmetry. Okay, and so then we have this conjecture that the symmetry in n-dimensional space, I mean n-dimensional graph, are classified by the braided monodal n category, or more generally, braided tensor n category. Tensor really means this category may have an infinite number of objects, may not be finite. Okay. Certainly, if you more rigorously, we have to say, really only the holo-equivalent class of the symmetry are classified by the braided tensor n category. And also not all the n category is involved. Only certain n category basically is a center for monodal n category is involved. I mean all those n category is center of some kind of a monodal n category, and only this subset n category are involved in describing symmetries. So we give this kind of n category a name called symmetry braided tensor category, or SYM-BTC. And then we claim that this kind of a SYM-BTC replaces a group to describe a symmetry in quantum system. So that's basically the story I'm going to tell today.
Can I ask a quick question?
Yes, please.
The description of symmetries in terms of groups should be contained within this description.
Yes.
In terms of
exactly
categories, right?
Yeah, that's right. So let me describe in this example. Yeah, go ahead.
No, okay. So I just wanted to see how that comes about. So
yeah, maybe let me describe the example just now. Okay. So first, let's restrict ourselves to one-dimensional space. Well, in one-dimensional space, we don't need to talk about n category. We just need to talk about one category, which is much more familiar. So actually, I don't even know whether the precise definition of a braided tensor n category is given mathematically or not. But the one-dimensional, this one category is a much well-developed topic in mathematics. So we'll restrict ourselves to this one-dimensional space. Then we talk about the braided tensor one category. And the braided tensor one category have a name. It's also called this modular tensor category. This is the same thing as a braided tensor category. Corresponds to the non-degenerate braided tensor category. Okay. And so we are talking this SYM-MTC. And in this case, the symmetry described by a group, the one-dimensional quantum system whose symmetry are described by group G, will be described by this SYM-MTC, which is a quantum double of this group. Yeah, it's a quantum double of the group. That's correspond to the category describing this symmetry. But then we have this, beside the quantum double, we will have a twist quantum double. And the twist quantum double also describes some kind of symmetry, and which is a little bit beyond the group, and we call them anomalous symmetry when we have a twisted quantum double. And then there is we know this the symmetry the module tensor category can also be given by the I don't know, it's I don't want to call this the quantum double for Hopf algebra or this kind of thing, so those are all give this more general symmetry which can go beyond the group. Okay, and physically, to physicists, this category is very abstract. So we try to describe the category using some numerical data. So then we know how to handle them. For the modular tensor category, and we have this number n, which is describing the number of objects. That's one numerical data we need to characterize this modular tensor category. We also have a fusion ring, how objects are fused, NABC. Then this object may have a topological spin, which is just a face, U1 face. And also we may have an associator, and that's described the different order for fusion, different order for tensor product may be associated by some unitary transformation, which is some associator. And certainly there's an R symbol, but the R symbol is kind of included in this topological spin. So I won't talk about the R symbol. But basically there's some collection of data we can compute, and then to characterize this the braided modular tensor category. Okay. So let me try to explain how those kind of data arise from operator algebra. So basically, our task is we are given operator algebra, operator subalgebra, local operator subalgebra. How the local operator subalgebra can give rise to those data, then eventually give rise to a symmetric symmetry MTC. Yeah. So we know that when you have a continuous symmetry, like a U1 symmetry or SU2 symmetry, then there is a conserved quantity, some quantity which do not depend on time. And that's a famous Nurse's theorem, which associate every continuous symmetry to a conserved quantity or conservation law. But actually, a finite symmetry also gave rise to conservation. And we can call them discrete conservation law. But this discrete conservation law actually corresponds to fusion rule. So this NIJK, this fusion ring, actually describe a discrete conservation law. So this fusion ring describe a discrete conservation law. So let me try to explain how this was connected. And I will try to explain those connection by a single model. We call the icing model in one-dimensional lattice. So on every side, on every vertex, and we have a two-dimensional vector space, a Hilbert space. The basis is spin up, spin down. So this is what we draw, the spin system. So on every vertex we have a 2-degree freedom, spin up and spin down. And then we have a Hamiltonian is a sum of local operator. One of the local operator is just this X operator on I. So this operator just flip spin up and down, between up and down, just do the spin flipping. Then we also have this operator Zi times Zi plus 1. I label different vertex. So this I just 1, 2, 3, 4, 5, 6. I just label this vertex. And this Zi times Zi plus 1 means the two neighboring spin may interact. And the Hamiltonian eigenvalue of Hamiltonian is in physics called energy. Is energy. So this Hamiltonian with there's a minus j coefficient means that if two spins are both up on neighboring side, and this Zi, Zj, Z is this diagonal operator, 2 by 2 diagonal matrix. If both spin are up, then we have a 1 times 1, this two eigenvalue 1 times 1, with a minus sign means energy is negative, it's lower. So this Hamiltonian prefer the neighboring side to have two spins parallel to each other, either both up or both down. Okay. But the X want to flip them, so there's some frustration between this ZZ term and the X term. So that's make this model have a non-trivial dynamics. Okay, so Z is this 2 by 2 matrix. That's another operator, local operator, act on a single site. Okay, so in this particular example, our local operator subalgebra are generated by these two operators. This is Zi plus 1, and also Xi. For all different choice of I, these two set of operators generate this local operator algebra. And then this algebra really encode the symmetry of the quantum spin system. Okay. Then from this local operator algebra, how do we see the symmetry? How do we see the conservation law? One conservation law we can see is actually is domain war. Suppose we have this kind of a spin configuration. They all up for a while, then they become all down for a while, then all up. Then from up to down, we have this domain war. Sorry. Yeah, we have this domain war. For example, in this picture, I have two domain wars. And then here I claim that a number of domain wars are conserved, but only have a mode 2 conservation. And one thing we can see that the action of this pair Z operator, partly is a pair of Z operator to this configuration. They don't change because Z operator preserves spins. The Z act on up still gave up. Z act on down gave us a minus down, but still down. We don't flip spin. So therefore, Z operator act in this configuration, they do not change spin, so the number is preserved. And when you apply X operator to this configuration, we can see that a spin down, this spin down may become spin up. Then that means the domain wall may be shifted to the next point. So therefore, this X operator just move the domain wall around. But however, when two domain walls are next to each other, when you flip the X, then the domain wall may disappear. So two domain walls can annihilate. So that's why this local operator algebra preserve the number of domain walls, but only have a mode 2 conservation. So that's a wonderful conservation law we have. And we have another conservation law. And to have that conservation law, we need to choose another basis. You know, on each vertex, we have a two-dimensional vector space. And we can use the up and down as a basis. And we can also choose another basis we call the left or the right. So this is really the spin x direction, either to the positive x or negative x. They are superposition of these up and down spins. You know, this up and down spin give us a spin in one direction, in x direction, and the up minus down give us spin in the opposite x direction. So we have two directions. And in this new basis, this left-right basis, this Z operator would flip left-right spin. You know, Z operator flip right to left or left to right. But the X operator preserve a spin because these combinations are eigenstates of an X operator. So X operator do not change in spins. And in this case, we can take a reference state. So if all the spin point to the right in X direction, we call this a vacuum. There's nothing. Then if you have some spin point in the negative X direction, then we say there's something. Okay. So therefore, we call the something so-called Z2 charge. We call this something E. So here in this configuration, we have a two excitation, two E. One E is here, another E is here. Then the number of E also have a mode 2 conservation. Again, this X operator, you can say X operator do not change left or right. So they do not change the E. However, a pair of Z operator flip pair of spin. Let's say a pair of Z operator flip two spin here. Then that's basically moving this E excitation from one side to a neighboring side. So therefore, this ZI-ZJ operator is moving this E excitation around. And then two E excitation, if the two E excitation are next to each other, then we can flip them both, then annihilate them both. So they only have a Z mode 2 conservation. Okay. So the domain wall excitation I talked about a moment ago, let's call them M object. So we have an M object, I have an E object. They both have a mode 2 conservation. Okay. And then certainly we have a two object. We can imagine we have a tensor product or fusion of two objects. The E and M can combine. And then we get another object called F. Okay, that's just bound state of a charge and a domain wall, the E and M. And plus the trivial object, that's nothing, no excitation, is also object. So at the end, we find there's a 4 object. So that's how I get n equal to 4. So this symmetry are described by the multi-tensor category with a 4 object. And you also know their fusion rule. This is a monodal structure. This EE, MM, FF, they all annihilate. They just give us a trivial object, a unit object. And then certainly the EM give us F, and FM give us E, and EF give us M. So that's give us NABC. That give us a fusion ring. So this is So this is how we recover the N and the fusion ring. So now we start to see some shape of a category. But the category have other data, have the topological spin, have associator. But how do you compute the topological spin and associator from this local operator algebra? Okay, so this actually is a little bit tricky. And then to really compute other data for the modular tensor category, we need to introducing a notion of patch operator. In one dimension, this is just a string operator. And the string operator just means the operator act on many sites, something like that. So when the string is very long, this operator is not local, But on the other hand, when you apply local operator many times, we can generate pretty long strings. So this is a very important thing. Our local operator subalgebra actually contain pretty large non-local operators. And those operators play very important role in our calculation of symmetry MTC. Okay. And actually, among those non-local operator we call patch operator, there's a subclass of a patch operator, which is very useful. And it's called a transparent patch operator. Okay. This transparent patch operator basis following. So again, let's using one dimension as an example. In one dimension, we have an operator, a string operator, which a bunch of operators act on this string. But these string operators have very special property. They commute with all this small string operator, this local operator like this. They commute with xi and zi plus 1. They commute with this. So this transparent patch operator is they are non-local string operator. But however, the middle of a string commute with all the local operator. So they are transparent. They are not observable, as if they are not there, just like an identity operator. So because those middle string commute with all the operator we are interested in, all these local operator subalgebra, so they just behave like identity operator, just as if they are not there. So therefore, this transparent patch operator almost behave like two local operator at the end of a string. At the end of a string is a two local operator. So, but somehow they are not a local operator. So the end string operator for the transparent string operator give us a new sectors. Yeah, give us a new sectors. And this sector actually is correspond to object in the modular tensor category. So therefore, this transparent patch operator really is actually a more systematic, more formal mathematical way to define the object in the modular tensor category. Okay, and but however, not all the transparent patch operator correspond to object. There are some equivalence. For example, we can multiply some local operator near the end. Then modify the boundary by some local operator won't give us a new object. They became some kind of isomorphism. So they are not a different type of object, just isomorphism. And so therefore, mode out this multiplication of a local operator to the boundary, this equivalent class of this transparent patch operator actually correspond to the object. And for our example, we have a 4 equivalent class of transparent string operator in one dimension. One of them just a string of identity. There's nothing, so there's a trivial. Another is we can have a product xz, product x operator, which is spin flip operator from up down spin flip operator from I to j. So the picture is like this. So we may have a bunch of x multiplied together and give us this x string operator. this X string operator is a M, give us an M object. However, we can also have another operator, which is a pair of Z. You may think, why not a single Z? Why single Z operator is not allowed? Because single Z operator is not generated by the product of this X and the pair of Z. So we always have even number of Z. You can never have a single Z. But however, if you multiply a pair of Z sequentially, like from I plus 1, that's one pair. Then I plus 1 to I plus 4, that's another pair. Then when you multiply this string of Z pairs, then we get the middle of Z all annihilate, because Z squared equal to 1, they all annihilate. So then we left two well-separated Z, Zi and Zj. So this is another transparent string operator. And this string operator is transparent because between I and j, we have identity, which commutes everything. So that is easy. And the M string operator is transparent, is more non-trivial because in the middle, they have X operator. But however, this a string of X operator commute with both X and a pair of Z. So therefore, this one also transparent, but due to non-trivial reason. Then our F object, which is bound state of E and M, basically the product of this E operator, E string operator, and M string operator. So that gives us this F object. So therefore, to classify this transparent patch operator would again give us a number of object. And the end of string corresponds to this object. And this string operator basically moving the corresponding object, like this Z operator. It's operator moving this E particle around from I place to J, from I side to J side. And this M string operator moving domain wall from I side to J side. So they are just moving this object around. Those string operators are those kind of like we call hopping operators. Okay. Then this string operator satisfies some operator algebras. Like two E string operator, when you multiply together, you get a one string operator. And two M string operator multiplied together also give us a one string operator, and etc. So this can encode the fusion rule of the object. Okay. So from the fusion ring, we can get this. And also we can join two strings. You know, the string ij and the string jk can be joined, we multiply them together, can be joined between string from jk. So that's describing by this. So those it has some algebra. Okay. Then there's but once we have this string operator describing those objects, then we have something new. That is this kind of structure. Okay. Yeah, maybe let's describe this structure. You know, we have a short string which are covered by a long string. This string operator would commute because a short string is a product of this local symmetric operator. So they all commute to the middle of the string. So these two always commute. But however, if I have two string operators which are straddled this particular fashion, then they no longer commute. And their commutarization became very interesting. And for our case, like E string operator and M string operator, when they straddled in such a way, they anti-commute. They give us this minus sign. Okay. This minus sign have a holographic explanation. We can go one higher dimension, like go 2 dimensions to understand this minus sign, because these two are different ordering of a string operator. We can view different order as some order in time direction. So first we have this E string first and M string later, or M string first, E string later, and then we can view these two. We can compare these two different ordering as in this graph as if this M particle go around the E particle once in this one actual dimension. Okay, what I really try to say is that this commutation relation can be viewed as a double braiding between E object and M object in one higher dimension. Certainly in one dimension, we cannot do braiding. But however, the operator algebra have operator ordering. We can view operator ordering as time ordering, then view this as a braiding, and then they have this double braiding. And this double braiding is a concept defined in the modular tensor category. Object in modular tensor category can braid. One object can go around another object, and this double braiding between E and M is non-trivial. And in the operator algebra sense, it's determined by this minus sign for this transparent patch operator or transparent string operator when the two string operators are straddled in such a fashion. Yeah, I think this is a very important example. So we start to see this the mall feature of a modular tensor category can be extracted using the algebra of a transparent string operator. And so this is the key. Once we're using local operator to construct transparent string operator, then from algebra's transparent string operator, we can go on to extract data to describe modular tensor category. Okay. So this is this is really the main point. And the other thing is more technical, so I won't explain in more detail. I just want to say that associator means that the three objects may fuse in different order. Say we can fuse AB first or fuse C later, or we can fuse BC first and fuse A later. And this different fusion can be described by the different ordering of this open string operator. You remember string operator just hopping. So here the vertical direction is time direction. So that's describing this the hopping different operator ordering. And then you can see this here in this graph, the AB fuse first, and this graph BC fuse first. But this different order fusion can be viewed as a different arrangement of hopping or different arrangement of the string operator. And so therefore, so this different arrangement of the string operator may have additional phase factor that gives us F symbol. So this the detail is not important, but the idea is that from the operator algebra of those transparent string operator, we can extract F symbol. Similarly, the mutual statistic, self-statistic can also be extracted this way, like this way. We maybe have a two object A and A. And for this arrangement of hopping, you can see these two A exchanged. That gives us self-statistics, or this theta A. And then this A and B may go around the A once. So that corresponds to what we discussed. These two string operators straddled in different way, have different order, and this gave us double braiding. Yeah. So using this idea, we can extract the full modular tensor category. So this is certainly this very simple example. And right now, actually, we don't have a very comprehensive theory to do this general, but we believe this can be generalized, and the whole thing can be developed. I think there's some mathematicians paper may do something along that direction, and which I need to learn and study. But let's just accept this that is some kind of modular tensor category actually describe a symmetry in one-dimensional quantum system. Then let's just say, what kind of symmetry do we have in one-dimensional quantum system? Well, that became a classification of modular tensor category. So actually, in this paper, we did some classification modular tensor category up to rank 12, and so it's a pretty extensive calculation using GAP computer algebraic system. And so like at the rank 12, we have a 221 modular tensor category, which are unitary. But however, among these 221 modular tensor category, only 3 of them are center of a fusion category or center of a monodal category. So only 3 of them correspond to symmetry. And at rank 4, we also have a 3. We have 18 modular tensor category, but only 3 of them it's a center of something, so they correspond to symmetry. And for these three at rank 4, okay, maybe let me yeah. Oh, okay, yeah. So so then you may say the following, so what? If using multi-tensor category to describe symmetry, what the use of it? Okay. And one application of the multi-tensor category is that we can use it to classify so-called gapped phase of matter. This is a very important physical question. There's some matter with energy gap, some matter don't have an energy gap. So this is one class of matter with energy gap. We can cluster them if we know the symmetry. The gapped quantum matter basically describes a spectrum of a Hamiltonian. If spectrum is like this, there's a window in the spectrum. And this window do not close as the system size go to infinity, as the number of vertex go to infinity. Then we say they have an energy gap. If there's no spectral window as the system size go to infinity, then we say there's no energy gap. And the system with energy gap are very simple. And so we have a very good theory about it. It turns out that for system with a certain symmetry given by this multi-tensor category M, and from this multi-tensor category M, we can compute the so-called Lagrangian condensed algebra. This is another thing in the category theory. Mathematicians just define there's a such thing called the Lagrangian condensed algebra. It turns out that the Lagrangian condensable algebra one-to-one classify all the possible gapped phase. So this is really, for physicists, this is really very impressive because the gapped phase have strong interactions, very hard to compute, almost have no clue how to classify them. But once we understand the symmetry in such a way, we suddenly have a conjecture. I think this is not proven, but we believe there's a conjecture. The Lagrangian condensable algebra classify all gapped phase. So this became quite a non-trivial result in physics. And for example, at rank 4, we have three symmetry MTC. And one of them is just Euro Z2 symmetry. That's the example we just discussed. Another we call the anomalous Z2 symmetry. And the third example is a non-trivial, is double Fibonacci. This one is beyond the group. This double Fibonacci is really beyond the group. And then using our classification of gapped phase, we say that for Z2 symmetry, there's two gapped phase. One gapped phase are symmetric phase where all the spin in x direction. So this is a non-degenerate symmetric phase. And another gapped phase is just up and down. So that there are two degenerate, the ground state have twofold degeneracy. One of them is spin all up, another of them is spin all down. So there are twofold degeneracy of the up and the down spins. And for anomalous Z2 symmetry and for double Fibonacci, the classification is very simple. There are only single gap phase in this case. So this really became very non-trivial results. And there's another application. Let me do this. At rank 8, we have S3 symmetry, which is a group, group-like symmetry. S3 is a permutation group of 3 objects. And for this symmetry, the MTC is something with a rank 8. So it's a quantum double for S3. And here I want to mention that this quantum double S3 have an automorphism. There's exchanging this A2 object and this B object. Exchange these two objects, this MTC remain unchanged. So there's automorphism. And this automorphism also have a physical application because the S3 symmetry have a 4 gapped phase. These 4 gapped phases are labeled by their ground state degeneracy, like 1, 2, 3, 6. There's 4 gapped phases. And we may have phase transition between those 4 gapped phases. For example, we may have a transition between phase 2 and phase 3, or we may have phase transition between phase 1 and phase 4. But very interestingly is that using this Lagrangian algebra, and also to see, we can identify how the automorphism act on phase 1 and phase 2 and phase 3, phase 6. It turns out that the automorphism really exchange phase 1 and phase 3 and exchanging phase 2 and phase 6.
Xiao-Gang.
Why this is important? Yes.
Yes, I gave you another extra 2 minutes for that unfortunate interruption, but I think you're starting to break into your question time now. So
yeah, so yeah, I'm finished. Yeah. So
okay.
this means that the transition between phase 2 and phase 3 and transition between phase 1 and phase 4, 6 are identical. They are related to the this automorphism of MTC. So physically, they are means these transitions described by same critical theory. So again, a very important application in physics. So therefore, at the end, we say that the symmetry is an important physical phenomena, but the group have a long story. We have the group was developed probably based on to try to solve polynomial equations, and then we will start to describe the symmetries. But that's kind of 100 years ago, and 100 years later, we learn more, and we find that there's a quantum symmetry are go beyond group. They are really described as a unitary braided tensor higher category. Yeah. So this kind of new way to look at the symmetry really changed our perception a lot, because symmetry plays such an important role in physics. And that's basically this new perception of symmetry basically changed our landscape. Yeah. Thank you very much.
Great. Thank you, Xiao-Gang.
Yeah.
Okay, so we have time for questions. If you have a question, feel free to just, I don't think anyone can unmute anymore. So if you have a question, press the react button and I'll call on you. Sorry, in React, there is raise hand. So press that. Kevin, okay. Maybe Kevin can unmute because he's a co-host, but go ahead, Kevin.
Hi, thanks for the talk, Xiao-Gang, and sorry again about that interruption. We'll discuss whether we need to change anything about our security settings on here. But really interesting. I wanted to ask about you gave a table of computations of, it looked like classifying all modular tensor categories up to 12 simple objects or something like that. A couple more slides back, I think. Yeah, right there.
Yeah, this one.
So I just want to ask about the computational problem there. It's not obvious a priori that this is even there's no obvious algorithm to classify these, right? You're doing something quite non-trivial to be able to actually.
No. I sorry, I cheated here.
Okay.
Okay, let me describe the computation a little bit more. And so actually, we did not compute the modular tensor category. We classify so-called modular data.
Right.
And that is doable because we don't know how to handle F symbol, R symbol directly. But the modular data, this S and T matrix are easier. They are cyclotomic numbers. So they're much they're under control. So basically what we classify is actually all this modular data.
Sure.
And then and also mathematically there's also tricky because for modular data we only have some kind of necessary conditions. And I think we don't know the necessary and sufficient condition on modular data. So therefore our classification may have fake results.
Right, right. Okay, so this is an upper bound.
Yeah, this is upper bound.
Yeah.
So they are necessary, they are upper bound. Yeah. And in particular, since you raised the question, there's a one result at rank 12 with a very high total dimension. I think 3,900 something. We have no clue what this corresponds to. And also at the rank 11, also there's a one, the one with highest quantum dimension, I think the D square is like a 1,300 something. I don't remember exactly. That's also, we have no correspondence. But that's only two. And for other things, there's some other modular data. We also don't know exactly what is the correspondence of modular category, but there are some ideas, there's some clue. It may correspond to certain things, but we are not absolutely sure. But however, for rank 11, rank 12, there's a two example, maybe under their relatives are totally clueless, so we're really wondering, are are they fake? Or if they're not fake, then it's really new one. There's no known correspondence. At the rank 12, our collection include hardware. Hardware is something more unusual, but the hardware is there. And but there's one even beyond hardware.
Yeah, very intriguing. Thanks for that clarification. I studied just a little bit of vertex operator algebras a decade ago, and I thought I remembered it being extremely hard mathematically to really be sure you got a modular tensor category. So that seems consistent with what you're saying.
So we don't have a. I'm happy I'm a physicist, so I can say this. As a mathematician, I cannot say this.
Yeah.
But for the physics, we are pretty happy because rank 12 is not so high. So very likely they probably that's all. And then for us, we want to know this because then we can really study individual field system. They may correspond something in the table. So we know where are we. Yeah. But for the rigorous mathematical classification, we don't have it. And the main trouble is that the F symbol have a gauge dependence. They are general complex number. They are not even number theory numbers. So whole thing became more difficult. Yeah.
Okay.
Thank
you. Thank you, Kevin. Thank you, Xiao-Gang. We have another person, Deepak. Go ahead and
yeah.
Yep.
Yeah. So hi, Professor. So I have two. My question has two parts. The first is, how do we understand the emergence of continuous symmetry groups from this framework? And then the second part would be, what is the possible implication of this kind of a framework for, let's say, construction of standard model of elementary particles in terms of some sort of
Yeah, both questions are really, really good questions, and that's things we are thinking all the time. For the continuous group, you notice I only describe a discrete symmetry. And because discrete symmetry, the number of representation is a finite. So that means the number of objects is a finite. Okay. And for continuous group, the number of representation is infinity. So therefore, the symmetry category for continuous symmetry must be, I cannot say infinity category because that's name already used. So I have to say tensor category means infinite number of objects. And here, as a physicist, we have a huge headache. We have no idea what those things. So we're really hoping mathematicians developing this kind of category with infinite object. And this is really the main problem we have. And so we feel there should be a very nice theory over there, but the mathematical side is not fully developed. That's my understanding. So we cannot just take the mathematical theory and apply it to our physical system. And we wish we really wish there's something like that. We can learn that and then apply this. Or maybe we have to develop this kind of thing ourselves. But for some symmetry, like a U1 symmetry, maybe it's not that hard. For general continuous symmetry, maybe it's hard. But for some symmetry, maybe it's not that hard. Maybe too. But on the other hand, there bound to be my feelings that there bound to be new structures. Yeah, there's a new structure beyond beyond the structure we are familiar with a monodal category. There should be something new, unusual for the continuous version, and so there should really non-trivial. And then how to use this theory, like in the standard model of particle physics. Let's consider some simpler question. That's in this case, we classify, we say we have a classification of we have a classification of a gapped phase using this Lagrangian condensed algebra. Yeah. But for standard model, for many other systems, there's also a gapless phase. The gapless phase is much more non-trivial. and it's more interesting. And actually, that's our main motivation why we studied category to describe symmetry. Because a gapless phase may have an emerging symmetry, some symmetry which only appear at a low energy. The emergent symmetry is very non-trivial, very general. Now we see that this emergent symmetry in gapless system are really described by the symmetry BTC, this braided tensor category. And then that may give us a entry to really systematically study and even classify gapless phase and gapless system. And this is again is ongoing, and most emergent symmetry are continuous. So we may have trouble. But for some simple things, simple gapless system, this program seems to work well. We can classify gapless system. And the standard model gapless system, in a sense, all the mass of a proton and electron, they are much less than the Planck scale, by factor of 10 to the 20. So if you ignore the proton mass, electron mass, we can view the standard model as a gapless system. And then using this emergent symmetry to classify this gapless limit, then open up a little bit of gap as a perturbation. So this maybe this is the way we can get a very systematic non-perturbative understanding of every gapless system and including standard model. Yeah.
Okay, thank you very much. I think we're going to end the live stream here. And thank you again, Xiao-Gang.
Yeah, thank you.
And okay, so the live stream is done. The recording is